Okay, hello. So I hope everything's all right. We are nearly done. So we are going to have your last quiz on Monday. Okay, so we try to give you a couple of more topics. Then, as usual, the quiz is going to be I post a quiz and you do it and you submit it. Okay, so what I'm going to do today is I'm going to give you a nice application of these eigenvalues. Okay, and it's a little bit of a calculus, but not much. You may have seen it before if you have done the differential equation course, but otherwise, we are not going to get into details, just a general idea of how we're going to apply the eigenvalues and eigenvectors in order to solve a very easy system of differential equation, and not very much like the one that we do on those courses. Okay, so it's a nice and short one, and we give you just a couple of questions on the quiz, and that would be very, very useful. Okay, so it's a part of 5.4. So I try this one and I'll give you as an application. There is this, just getting this one done. My method is very similar to your book base. It's easier because it's not like a differential equation course, of course. Okay, so we did those complex eigenvalues and the complex eigenvectors the other day. Okay, so let's see what is going to be this section about. So it's going to be 5.4. Okay, I check the assignment list. If I need it, I will okay, update it for you so you can be able, I think there are some problem from this section over there, but otherwise I will add it. Okay, so we want to know how we solve some easy, of course, system of the differential equation using the eigenvalues. Okay, so that's going to be a system of, you don't need much really, just being familiar with the exponential function, that would be enough for us. So a system of a differential equations. Okay, an equation that contains a given function and its derivative, we call it differential equation. But if you have a system of two unknown, two function and their derivative, then you are going to have a system of differential equations. Okay, so that's going to be the idea, and this is the notation that we are going to use. Okay, so suppose the functions you are going to have y1, which is equal to the y1 of x. It's going to be just a function of x. Okay, and y2 equal to the y2 of x. This is going to be the second function. They must be differentiable. Okay, so are going to be differentiable. Okay, they are going to be differentiable functions. Okay, they are going to be differentiable. So we are going to consider this system of the equation. Consider the following system. That is going to be a following system of course, a differential equation. Differential equation. It's very, very special one. Okay, so this is going to be a system that we have. We go with the y1 prime for the derivative of the y prime function. Okay, so it's going to be linear combination of the y1 and the y2. A y1 plus b y2. Okay, this is going to be the one. And the second one is y2 prime. Okay, y2 prime is equal to the c y1 plus d y2. As you can see, y prime and y2 are linear combination of y1 and y2. So the system that we're going to consider is going to be a system of a linear equation. This is going to be a system of a linear differential equation. Now what we would like to do, as we did it before, a system is given to you, want to change it into the into the matrix form. So the way we're going to do it, the unknown are going to be y1 and y2. So we're going to introduce some vector notation. So suppose we introduce the y to be just a function or a vector. This vector would be a two-dimensional one, y1 and the y2. Okay, this is going to be y, and of course y prime now is going to be derivative of the y1 prime, and this is going to be y2 prime. Okay, this is it, and so we need a matrix of the coefficients. So we introduce the matrix of the coefficient to be A. So that would be A, B, C, and D. Okay, so that's going to be the one. The unknown is going to be y1 and the y2. Then we have to find it. So if you go back and check the, okay, check the system. So this is what will happen. Then what we have to do is one should solve, if you like, or we should solve. One should solve. Okay, if you go back and write it down in the matrix form, this is going to be y1 prime, and this is going to be y2 prime in vector form. And this is going to be the product of, we have the AB and the, sorry, we have the AB and the CD over here. Okay, this is going to be your matrix A. This is going to be the matrix A times it by y1 and y2. So we change the system of the equation into the into the matrix form, if you like. Okay, so so this is going to be y prime. This is going to be y prime, and this is going to be a times y. See, so the matrix form, if you like, the matrix form of the given equation is going to be in this form. Okay, so this is what we're going to have. Now, this is going to be a kind of linear equation, if you like, from the differential point of view, differential equation point of view. And so it's like, you know, when it's a linear equation, it's like you are looking for a function whose derivative is going to be what is going to be just a multiple of the function, if you like. So for this type of a function, we can guess what is going to be the solution of this equation. The solution is going to be exponential function. So we're going to suppose, want to relate it to the, related to the eigenvalues and eigenvector, and try to find, you know, a method to solve it. Now, suppose the solution of this, suppose we would like to force the solution to be just an exponential function. So it's going to be a k here, okay, k e to the, let's say lambda x. Okay, suppose this is a solution of this equation. Okay, it's going to be a solution. This is going to be a solution of this equation that we talk about it, y prime equal to the a y. If this is going to be one of the solutions, of course, k is going to be just a vector. Okay, this is going to be where k is going to be a constant. It's a constant vector, if you like. It's going to be a constant vector over here, a constant vector, and the lambda. Okay, and lambda is going to be a scalar, is a scalar. Okay, so this is what we have here. So the lambda is a scalar. So what we would like to do is, since this is a solution of the equation, it must satisfy. So if you differentiate it, okay, it must satisfy the equation. Just go back and substitute to see if it does satisfy. Okay, so if you put it in this equation, what are going to happen? So you should have lambda times e to the lambda x. You have to differentiate it. Prime is equal to what? Is equal to the a times, then you have the k e to the lambda. Okay, e to the lambda x. So I just substitute in this equation that we are going to have. Now what we can do is we can differentiate it. K is going to be a constant and the derivative of exponential function. So it's going to be k. Okay, this is going to be k. You know that derivative of exponential function is exponential function, but you have to multiply u prime. This is like e to the u. So derivative of e to the lambda x is going to be lambda e to the lambda x. Okay, that give a derivative, which is going to be equal to, and on this side, just the scalar is this going to be just the same thing. It's going to be ak e to the lambda x. Okay, that's going to be the one. But you know that the exponential function never zero, so we can divide by e to the lambda x. If we divide by e to the lambda x, so the leftover is going to be k lambda, which is equal to the a times k. Okay, now if you move it to one side, if you move it to one side, it's going to be lambda, k lambda minus ak equal to the 0. And if you factor out the k, so this is going to be lambda I minus a times k equal to the 0. See? So we get some very nice conclusion over here. So the conclusion is going to be what? Conclusion is that the y equal to the, okay, y equal to the k e to the lambda x is going to be a solution of this matrix equation, okay, or solution of a system, if you like, if and only if what? If and only if lambda is going to be an eigenvalue of a matrix A with the corresponding eigenvector k. So that's it. So this means you are going to find the lambda. You know how to do it. You know, this is it. We just form the characteristic equation, and then we get the solutions. Okay, so the conclusion is that fact that, okay, so this is going to be the conclusion that we have is, so therefore, okay, therefore y equal to the k times e to the lambda x is a solution. Okay, so this is going to be a solution of a system, a solution of the system, solution of the system. Okay, if and only if lambda is going to be, lambda is an eigenvalue of the matrix A, the matrix of the coefficient, okay, of the matrix A with with the eigenvector, with the corresponding eigenvector, corresponding eigenvector k. Okay, so that gives us a hint of how we're going to solve this system of the equation. And you know that the matrix is a 2 by 2. So if you form a characteristic equation, your characteristic equation would be a quadratic equation. So when you have quadratic equation, the cases are that you may get two distinct solutions, one repeated solution, or two complex solutions. But we are going to just consider the case that they are going to be distinct. Okay. Okay. So that's going to be the one. So we consider the case only that the eigenvalues are going to be are going to be distinct. So if they are going to be distinct, okay. So if if lambda 1 is not equal to the lambda 2, okay, lambda 1 is not equal to lambda 2, are going to be our are going to be eigenvalues of A. Okay, eigenvalues of A. So what's going to be the case? Then, then each of these e to the lambda 1 x and e to the lambda 2x are going to be the solution of the equation. Okay, so then we can show that, or in general, when lambda 1 is not equal to the lambda 2, so these two solutions would be a basis. It would be a basis for all the solution of the system of the equation. So if this is going to be the case, then y is going to be just a linear combination. Okay, so this is going to be the case. Then y equal to a linear combination of these two. So it's going to be C1. The first solution is going to be something like k e to the lambda 1x. Okay, this is going to be the first one. Of course, this, we may call this one k1, and the second one is going to be c2, the corresponding, the vector that we're going to find, and e to the lambda 2x. So if k1 is lambda 1 is not going to be equal to the lambda 2, so this is going to be the general solution. Okay, is the general solution. The general solution of the of the system. So if the solution can be repeated, you have to modify this, and that would be rather a course, it's just differential equation type. So if you take that course, or we divide into three parts and we talk about it. In this course, we're just considering when lambda 1 is not going to be equal to the lambda 2, because there is another interpretation of this one in your book. The argument is going to be they try only to use diagonal matrix to do it, and you know that in case of diagonal matrix you need two distinct eigenvalues, two distinct eigenvectors. So these two must be distinct to be able to do it. But this we just give you a general idea. But for repeated one, you have to modify this one. For the complex one, it's going to be the same thing, but it's going to be very much involved. We just consider one case only. Okay, this one. Okay, so that gives us a hint. Okay, we just want to see quickly what is going to be the role of the eigenvalues. It's just the beginning, really, for this system of the equation. It's going to be quite interesting one to look into this system of the equation. So we have the roadmap, and we are going to do it. In your book, as soon as they get the lambda 1 and lambda 2, they are going to find these eigenvectors. You know that these eigenvectors, then they create the matrix P. They want to diagonalize A, and just give you a brief formula to do it. But it's the same thing. This is a more direct one because I want you to directly to see the result. Okay, but if you read that last argument of your book and you would like to do it on the test, I don't mind, but I prefer this one. Okay, so there you are. We know what to do. We get the plan. So let's do it. Let's see it. Example. And this is, of course, a general solution because you have this constant C1 and C2. So these two vectors are going to be a basis. is going to be a basis for the subspace of all the solution of this system of the equation. So that's why we get a linear combination. Sometimes they may give you some initial condition, then you'll be able to find the C1 and the C2. In that case, your system is going to be, okay, your solution is going to be a particular one. I did it for the two variables. There is one question, one problem in your book. They do it 3 by 3. Okay, system of 3 equation. 3 by, it takes a little bit more time. So we just go with 2 by 2 by. It's nice to check that one too if you want. Okay, so that's it. We want to solve this system. Okay, solve a system of differential equation. Okay, the system of differential equation. Differential equations. We are interested in two, one with the general solution and the other one that you have to find a particular solution. We have both of them in your book and in your assignment. Okay, there you are. Let's take the first one. The first one is this system. The system is y1, okay, y1 prime is equal to the 2y1 plus 2y2. That's the first one. And the second equation is y2 prime equal to y1 plus, okay, plus 3y2. So this is going to be the system of the equation that we want to solve. Okay, quickly change it to the matrix form. Okay, so it's going to be the solution. To change it to the matrix form, your function is going to be y1 and y2 in matrix form, if you like, a column vector. Then your A is going to be your matrix of the coefficient, which is going to be 2, 2, 1, 3. So this is going to be the case. Now you have to find the eigenvalues of this vector. Okay, that was the idea that we talk about it. Okay, so form the determinant of, so what's going to be the det of, you go det of lambda I minus A equal to the 0. And in this case, this is it. This is going to be 2 minus lambda, 2 minus lambda, and this is going to be negative 2, and then negative 1, and lambda minus 3. The determinant equal to the 0. Okay. So we go, or the other way around. No, sorry, over here, it must be lambda. It's the same. This is a lambda minus 2. Lambda minus 2 minus 3, and we change those signs. Okay, so this is it. It's going to be lambda minus 2 times the determinant, lambda minus 3. This would be a positive 2 by minus 2 equal to the 0. So FOIL it, it's going to be lambda squared minus 3 lambda minus 2 lambda plus 6 minus 2 equal to the 0. So it's going to be lambda squared minus 3 minus 5 lambda. So minus 5 lambda and plus 4 equal to the 0. Okay, so this is going to be your equation, and then we are going to solve this equation. So what we're going to have is going to be lambda minus 4 times lambda minus 1 equal to the 0. So we get two solutions. I'm going to call this one lambda 1 equal to the 4 and lambda 2 equal to 1. Okay, so that's going to be the first step. The problem in this chapter, it's all end up with finding the eigenvalues and the eigenvectors. Okay, so we get the lambda 1 and the lambda 2, so we have to go and find the eigenvectors correspond to these two. You know that you substitute here to get those numbers. So let's go and find them over here. Okay, so the result is going to be, so we go for the first one. So I have the lambda 1. Okay, So the lambda 1 is equal to, lambda 1 is equal to 4. So I'm going to form the lambda I minus A times K, or times P. In your book, they use the P. K equal to this 0, and this is going to be the vector that we are interested in. Okay, if you go back and form that matrix that we did have, okay, so what's going to be, replace the lambda by 4, so it was lambda minus 2, so that give you 4 minus 2, 4 minus 2, and this is a negative 2, and over here you get the negative 1 and the 4 minus 3. So this is it times, you may call this one x1 or x2 or k1 or k2, it doesn't matter, okay, to get this number. So let's call it x1, and because I'm not going to call it x because it would be confused with the variable. Okay, k1 and k2, the lowercase k, equal to the 0. As usual, quickly you can find it. So this is going to be 2, negative 2, and this is going to be negative 1, 1. As usual, one of them is a multiple of the other one. Okay, so we don't have to continue. It's a k1 and the k2 equal to the 0. Okay, so I go with this one. So this is it. So that give me negative k1, and then plus negative k1 plus k2 equal to the 0. So the k1 and the k2 are the same. Okay, are the same. So I'm going to have the first vector. Okay, the k is going to be equal to, okay, this is going to be equal to the t, both of them. So the first vector is going to be tt. So we can pull out the t and introduce the first one. Okay, so this is the one. We may call it, this is going to be k1. So the k1 in this case is going to be the matrix 1, 1 in this case. Okay, so this is it. This is going to be, that's the case. Okay, so this is going to be k1. So we have to repeat it again for the other eigenvalues. The second eigenvalues is lambda 2 equal to 1. So get the second vector. So lambda 2 is equal to 1. Okay, lambda 2 equal to 1. So in the case are going to be, okay, so form that lambda I again. So what is going to be lambda I minus A equal to the 0. So go back, substitute. Lambda is 1, so that gives 1 minus 2. Okay, we get 1 minus 2, negative 2. And this is going to be negative 1. It was lambda, now lambda is 1. Okay, times again the vectors that give you 0. Okay, as soon as you simplify it, you will see there. So if you simplify that, give you a negative 1, and this is going to be negative 2, and then negative 1 and negative 2. Okay, so quickly you can change it into the 0, 0 for one of them. So again, we just go with the second part. Okay, I'll go with the second part. So they give you negative, okay, negative k1 minus 2k2 equal to the 0. Okay, equal to the 0. So we can solve for one of them, k1. K1 is equal to the negative 2k2. Okay, it's going to be negative 2k2. So, we can take the k2 to be equal to the t. So the k1 is negative 2t. So quickly you can get your second vector. Okay, I call it k2, which is going to be equal to, okay, so we get negative 2t for the k1. and this is going to be 2. So pull out the t. So you can get one of those basis 1, which is going to be -2 and 1. Okay, so the K2 is just pick 1. So the K2 would be a -2, -2 and 1. Okay, so this is going to be the K2. Now we are ready to give you the general solution of the, okay, of a differential equation. Remember the general solution, because each of these would give you one solution for the lambda 1 and lambda 2. Okay, you have a kind of a special solution if you like, but the general one is, you see we talk about it, so the y is equal to the c1 k1 e to the lambda 1, okay, lambda 1 x, and this is going to be plus c2 k2 e to the lambda 2x. So if you substitute, so your y is going to be c1, your k1 is going to be, this is k1 1 1, okay, 1 1 e to the lambda 1, which is 4x, plus, you get plus c2 plus c2 k2, which is going to be a -2 1 e to the x. Okay, this is going to be the general solution of your system, but quickly you have to pull out the y1 and the y2. Okay, because the unknown is y1 and y2. You can put them as a matrix form, and you get those two quickly. Okay, so I write it down here so that we have it, because you have to give us those. So what we have is y, remember, y is equal to the y1 and y2. Okay, so you have to pick over here and get the y1. So what's going to be y1? y1 are going to be the result of the first component. This is going to be c1. Okay, c1, it's a c1 e to the 4x. Okay, and plus, sorry, c1 e to the 4x minus. Okay, the second component is going to be minus 2c2. Okay, 2c2 e to the x. That's going to be your y1, and the y2 is similar. It's going to be c1 e to the 4x. Okay, and this is going to be plus c2 e to the x. So these are going to be the general solution of your system. It's a very nice nice application that you're going to have. The one in your book, the way they do it is they just use the diagonal matrix. We talk about it, and it's the same thing. It's the same thing because they do everything up to this part. You have to find the K1 and the K2, but this is quick. You don't have to worry about those type of arguments, and you get it right away. But the job is going to be the same thing because you have to find these eigenvalues and your eigenvectors. Okay, stay with the distinct solution. If it's going to be repeated solution, you will get only one of these eigenvalues. Then you have to create so you get only one eigenvectors. So you have to create the second one yourself. If you have done differential equation, you know how to do it, but we are basically interested in the nature of the problems, not those type of classic differential equation. Okay, so this is one. Your extra job is going to be, you have two on your book. And sometimes they give you initial condition. When they give you initial condition, you are not done. You have to impose those initial conditions. They give you something regarding to the y1 and the y2. Okay, y1 of 0 is 1, y2 of 0 is. So I'm going to give you one of that format too. So be ready for both of them. And then this is all we need to know from this section. Okay, it's just solving the differential equation using eigenvalues. So let's give you one with the initial values. so that you know how it takes to get the last part. Okay, so that is going to be part B. Part B, this is going to be a system of the equation. You have a y prime. Okay, y prime is equal to the y1 plus 3y2. That's a y1 prime, and this is going to be a y2 prime, and the y2 prime is 4y1. Actually, it's going to be 4y1 plus 5y2. This is the system, but they give you initial condition. The initial condition is that y1 at 0 is equal to 5. Okay, y2 of 0 is equal to the 6. So when you see this initial condition, this means that you have to go at the end, you have to find that C1 and C2 that we talk about it, okay? So the method is going to be the same. So we find the general solution and then we take care of those constants. Okay, so it's going to be the solution. Okay, solution, you just introduce the y. Okay, the y is going to be y1 and y2. Then your matrix A. So the matrix is going to be 1, 3. Okay, that's it. 1, 3, 4, 5. This is going to be the matrix. Okay, go for it. Lambda I minus A. So we have to find the determinant of lambda I minus A equal to the 0. So you are going to form that determinant. Okay, so it's going to be, this is it. It's going to be lambda minus 1, negative 3, and this is going to be a negative 4, lambda minus 5. Okay, lambda minus 5, just use cross multiplication to get the determinant. Lambda 1 times lambda minus 5. That's going to be a positive 12. We make it negative 12 equal to 0. Okay, foil it. So if we did that, give it lambda square minus 5 lambda minus lambda plus 5 and minus 12 equal to the 0. Okay, equal to the 0, and then this is going to be lambda squared. So minus 6 lambda, and this is going to be minus 7 equal to the 0. Okay, so take care of this one. So this is going to be lambda minus 7 times lambda plus 1 equal to the 0. So we have two solutions. Lambda 1 equal to the 7 is going to be the first solution, and the lambda 2 equal to the negative 1 is going to be the second solution. Okay, so that give you lambda 1 and lambda 2s, and go and find the corresponding eigenvectors. Okay, so I go with the lambda 1 equal to the 7. So I form the lambda I minus A times K equal to the 0. Okay, so go back, lambda equal to the lambda 1 equal to the 7. So it's going to be 7 minus 1. Okay, 7 minus 1. And that's a negative 3. This is going to be negative 4. And the 7 minus 5. Okay, so this is going to be a matrix times it by, K1, K2, which is equal to the 0. Quickly, you get the 6, negative 3, and this is going to be a negative 4 and 2. Okay, negative 4 and 2. So times it by lambda 1 and lambda 2, which is equal to the 0. Okay, so this is going to be the case. It's going to be 6, 2. Okay, so it's going to be the same thing. If you divide by 2, you will see that they are the same. Okay, this is it. So divide this one by 2, that give you, or divide by 3. If you divide, you don't need it, you just apply one of them really. But if you divide by 2, so that divide by 3, that give you 2 and -1. And you do the same thing over here, it's going to be 2, -1. You don't need it, you can simplify the K1 and K2 and just do the job. Okay, so I go with this one, that give me 2K1. 2K1 minus K2 equal to the 0. So that gives me the fact that the K2 is equal to the 2K1. Okay, so we take the K1 to be equal to the T, and the K2 would be 2T. Okay, so your K1, we can write it down here. So the first one is going to be, okay, it's going to be the T and the 2T. Okay, 2 and the 2T. So it's going to be T times 1, 2. So you can take your K1 to be 1, 1, 2. Okay, this is going to be the case. So we go on, we do the same thing to find the, okay, so that was the lambda 1 equal to the 7. We get lambda 2 equal to the -1. Okay, so we go for it, and this is it. We have the lambda 2 equal to the -1, and the same thing. Okay, so lambda a minus a times k or x equal to the 0. And we go and check. Okay, go to us, just it's going to be the determinant. Replace the lambda by -1, so that gives me -1 minus 1. That is a -3, and you have a -4, and this is a -1 minus 5. Okay, times a K1, K2 equal to the 0. So that gives us a -2 here and the -3. This is going to be a -4 and the -6. Okay, so this is going to be the case. So if we divide the second one by 2, that gives you the first one. I just use the first one, to take care of it. So this is it. So I'm going to have a -2K1. Okay, -2K1 minus 3K2 equal to the 0. Okay, equal to the 0. So just take one of them to the other side. So how about 2K1 equal to the -3K2? So the K1 would be -3/2 of the K2. Okay, you can take the K2 to be equal to the 2T, just to get these numbers. Okay, so this is it. So this is going to be your K, the second vector, is going to be the K1 -3, okay, 3, 2 of the T, and this is going to be T. Okay, so just simplify it. You can take the T to be equal to, okay, T equal to 2. So your K2 is going to be -3 and 2. Okay, you need only one vector. So this is going to be your K2. Okay, so we have that's the K2. Remember that was the K1 was there, 1 and 2. Now we can get the linear combination of these two to get our general solution. Okay, so what's going to be the general solution? Y equal to the C1. Remember C1 K1, C1 K1, K1 1 2 e to the lambda 1 7 7x. So that's going to be the first part. plus C2, K2 is a negative 3 and 2. Okay, negative 3 and 2, and this is going to be e to the, okay, it's going to be e to the lambda 2, which is a negative x. Okay, so that gives you C1, 1, 2, e to the 7x. So this is going to be the general solution. Okay, this is going to be the general solution. So you pick your solution out. So your first solution is going to be y1. y1 is going to be c1, the first row. c1 e to the 7x, okay, minus 3 c2 e to the negative x. This is going to be y1, okay, and the y2 is going to be 2 c1 e to the 7x, and over here it's going to be plus 2 c2 e to the negative x. So these are going to be the general solution. Okay, but in this time we have we have the initial condition. So we have to apply that initial condition to get the result. So the initial condition is that the y1 of 0 is equal to 5. You go to the y1 and replace the x by 0. Okay, if you replace x by 0, so that give you c1 minus 3, c2 is equal to 5. Okay, for the initial condition y of 0 equal to the 5. And your second initial condition is y2 of 0. Okay, y2 of 0 is equal to 6. So again, you substitute x equal to the 0 here. So that give you 2c1 plus 2c2 equal to the 6. Okay, so we have a kind of a system of two equation, two variable to solve. Okay, to get these numbers, it's going to be easy to solve. Okay, if you like, you can multiply the first by -2 to just cancel it out, or cancel the second one. So it's going to be c1 minus 3 c2 equal to the 5. I divide this one by -2, negative c1, negative c2, negative 6. Okay, so if you add, so that would be 0, and this is going to be negative, okay, negative 4 c2 equal to the negative, oh, I didn't divide this one, so that's a negative 3, sorry. So now that give me, okay, this is going to be 2, 2, 2. I divide this one by -3. So the -3, and so this out. So that gives us a 2. Okay, so that would be the 2. So the C2 must be -1/2. Okay, double check it again. It's y0 C1 minus 3C2 equal to the 5. And over here, that give me 2C1 plus 2C2 equal to 6. And I divide by negative, everything's all right. So the C2 would be, okay, the C2 would be -1/2. It's going to be -1/2, and then substitute here. Okay, so we have a C1 minus 3 times the -1/2 equal to the 5. So it's going to be C1 plus 3/2 equal to 5. So the C1 is 5 minus 3/2. Okay, so the C1 is going to be 7/2, yes? 3.5. 7/2. So double check it. So then you just go back and substitute for the C1 and the C2. So your Y1 is going to be equal to the 7/2 of e to the 7x minus 3c2 minus, okay, 3/2 of e to the negative x, and the y2 is equal to the 2c1, which is going to be 7 e to the 7x plus 2c2, which is going to be minus e to the negative x. So this should give you the, okay, the particular solution of the system of the equation. Okay, nice application. We just wanted to see that the quick application, if you like, of these eigenvalues. And as I told you, you have to modify it when we get to the cases that you get the repeated solution or the complex one. But this is just a linear algebra course. This is going to be the one that for those courses. Okay, so this is all we need for the 5.4. So what else we can do or we are going to do? You see, remember we talked about the inner product on the Euclidean space Rn before. So at that time we just did it for Rn. We can do it in general for a general vector space. So just give you a little bit of those ideas. It's very important if you want to continue working in linear algebra, you need so-called inner product space. So the situation they're going to have, it's going to be similar because inner product is a kind of function. So I'm going to just give you a little bit of those type of ideas for the rest of the course. Okay. So just a couple of I post another recording for you. So just initial definition of, you know everything about it because we did it for the okay, we did it for the Euclidean space, so it's very similar, Cauchy-Schwarz, that give you a nice idea how from a classic case you can generalize something to the general case. Okay, so that would be another kind of good experience really to see how these concepts are going to be connected to each other. Okay, but not very much. Okay, and then we give you that quiz. Okay, that's it. Have a good one. Take care. If you need anything, okay, email me. Bye-bye.